So finally, we get to talk about the different groups. Mind you, this is just going to be a selected few, namely the alkanes, alkenes, and alkynes that we'll talk about. There's actually a lot more than that in organic chemistry, but just to keep this kind of concise, I decided to stop right at that point. Alright, so alkanes, I kind of implied this already, but alkanes are structures where you have a full saturation. Your index of hydrogen deficiency is equal to 0. And simply put, you just basically draw these lines. You could have branched um, type of structures where you have extra carbons coming from the middle, but technically speaking, these are just single lines. Single bonds are present. So all you should have in your structure for this to be considered an alkane is CH bonds and CC bonds. No multiple bonds and no oxygens. The oxygens actually kind of change the functionality of this thing to something else. But linear alkanes, as you may have already guessed, have a formula of CnH2n plus 2. And it's because of this that in the IHD formula we use the 2n plus 2 value to calculate the saturation point, because the linear alkanes are the ones that have the most hydrogens. Linear alkanes will always have the most hydrogens possible for any amount of carbon. Uh, but you also probably have gotten the impression that having a linear molecule is not always the option. Sometimes the molecule could be cyclic, in which case, in this case, if all the bonds are single bonds, like we saw here for the regular alkane, then this is now called a cycloalkane. And once again, you only have carbon-carbon bonds or carbon-hydrogen bonds, but the molecular structure is cyclic. And what it also means is that you have pretty much a formula of Cn with H2n. So you actually reduce the number of hydrogens by a value of 2, which tells you that you basically have a deficiency of 1 for your hydrogen count. The last part is what we call the haloalkane or haloalkane. Here you basically have a regular alkane, but in addition to your carbon-hydrogen bonds and carbon-carbon bonds, you also have carbon-halogen bonds present. It's still considered an alkane, but now it has halogens in it. And so your formula kind of extends a little bit more. You have n number of carbons, 2m plus 2 minus m number of hydrogens, and the m gets taken up for, by your halogens, which is the reason why we count hydrogen and halogen together as, equivalent. Alright, then we have the molecules where a double bond is present. These are known as the alkene family members. And the alkenes contain at least one carbon-carbon double bond. You could have more, but as long as you have one present, you already have an alkene. The formula for alkenes is CnH2n, which means that you have an index of hydrogen deficiency of 1. And you, of course, have the same possibilities for the alkene. You could have a cyclic alkene, or you could have an alkene that contains a halogen in it. And the possibilities are basically the same. If you make the alkene cyclic, then you decrease the hydrogen count by an additional 2 hydrogens. So now you have an index hydrogen deficiency of 2. Introduce halogens, the index of hydrogen deficiency remains the same because the halogens replace the hydrogens and kind of remain equivalent. Alright, and then you have the molecules that contain a triple bond in it. We know and determine these molecules, we basically call them alkynes. And aromatically, having that triple bond has a count of hydrogen of 2n minus 2, which is 4 less than the maximum, and therefore the index hydrogen deficiency for alkynes is 2. Now, as far as cyclic compounds, not to say that you cannot have them for alkynes. In fact, cyclic alkyne molecules do exist, but they tend to be rather large. And I'm probably not going to be focusing too much on those large molecules in this lecture. So I decided to just keep it simple and say if you have a cyclic ring present, most likely than not it's going to be outside of the triple bond, or the triple bond will be outside of the cyclic ring. This will be true if the cyclic ring has values of 3, 4, 5, 6 in terms of content. There's not enough room available for those bonds to achieve the sp hybridization of the triple bond if you only have a 3, 4, 5, 6 member ring. So if there is a ring, most likely not will be outside of the triple bond. And your halogens, you could have them either on the triple bond itself or somewhere else in the structure. And of course, having that extra ring means that you have an additional index of hydrogen deficiency. So this molecule, if you do the count, will have an index deficiency of 3. Whereas the ones with just linear alkynes, whether they have halogens or not, the count will still be 2. Alright, the last molecules that we are going to talk in this class are benzene. I already showed benzene molecules in the last example for the isomers. And your benzene molecule is simply a 6-member ring with 3 double bonds, alternating, from, double to single, double to single, double to single. And then you could also place halogens in them to get your halobenzene molecule. So we're going to look at all of these particular derivatives in this class. All right, let me talk a little bit about boiling point trends, and then we'll at that point move on to the nomenclature aspect of the lecture. All right, so looking at your linear alkanes as well as branched alkanes, the ones that have the extra carbon sticking out from the middle of the molecule, what you do see here is in red, this is your linear alkane. In blue, you have your cyclic alkane. And then, your branch alkanes are either purple or green. But what you can see very clearly is that the boiling point decreases as the surface area, the length of this molecule starts becoming more compact. We kind of talked about this in the intermolecular forces lecture, but you see it here very neatly, for a carbon count of 2 up to 10 carbons, right? So you have linear, branched, doubly branched molecules, and the boiling points decrease as the number of carbons starts increasing, coming out from the middle, branching out from the middle. The interesting aspect of this is that you have your cyclic alkanes, which are actually higher in boiling point than any of the other linear alkanes. And you kind of see a similar trend for the alkenes. You can have a cyclic alkene, which is higher in boiling point, generally speaking. You have your linear alkenes, which generally speaking are higher in boiling point than your branch alkanes in this case even. And the idea right here is that the more surface area your molecule has, the more intermolecular forces your molecule will contain. So you basically end up increasing the value for the boiling point. And here for comparison's sake, I'm showing you what happens when you have the double bond, at the end, if you have it in the middle. Sometimes there is a little bit of a change, but generally speaking, they tend to be roughly the same. There's not a lot of difference between the boiling points of having that alkene in the end or in the middle. Obviously, there's some changes, from example to example, but as you look at the trend, the changes are very minimal. The other thing that I kind of like to show, because it's kind of neat, is that when you look at the alkane, the alkene, the alkynes, and even molecules known as ethers, which we're not really going to talk too much about in this class, but I want to depict the intermolecular forces present in them to come up with some trends. The alkanes, alkenes, and alkynes only contain carbon, and carbon-hydrogen bonds, so they are non-polar by default. The ethers, however, have a carbon-oxygen bond, and that's the only oxygen present, so they actually have a dipole present. So dipole forces are simply stated, present in ether molecules. So just by that logic alone, you would expect ethers to have higher boiling points than any of these molecules down here. But what you can see is that your alkynes have a little bit higher boiling point, at least when the molecule becomes small in length, followed by the alkanes and then the alkenes. But then as the size of the molecules progress to higher and higher values, basically all 4 of these molecules kind of converge to the same thing. There's almost no difference. Right here you had some, noticeable difference, noticeable difference, noticeable difference, and then they kind of converge to the same value. And the reason why is because this is all about the chances that you get to see positive charges with negative charges. So Your alkanes, they just kind of attract themselves with London dispersion forces. Alkynes, same idea, but usually is triple bond next to triple bond where the biggest interactions happen. For the ethers shown right here, you have your actual delta pluses and delta minuses based on your polar bond. But as you make the molecule larger and larger, the chances that this carbon-oxygen bond is going to see another carbon-oxygen bond becomes less and less. And so ultimately you end up kind of diluting away this interaction and making it less likely that these two bonds will see each other. And so you kind of go back to the alkane case where, you know, anything in the structure will kind of just do in terms of attracting the molecules to each other. So you kind of dilute away, in a sense, the presence of that polar bond in the ether molecule, which is why you see that convergence of boiling points as we go to higher and higher values of carbon content. Um, yeah, so basically that polarizability is what's increasing the boiling point, right? At least for the ethers, but make the carbon content larger, larger, and larger, and you will kind of dilute away that dipole moment and kind of make them all relatively similar because the chances now become less and less that the dipole bond will see another dipole bond. Okay, so that kind of concludes the boiling point trend. There's obviously a lot more to be said about boiling points. So keep in mind your ideas of intermolecular forces from lecture 18. They will come in handy for problems in this chapter. Okay, now with that being said, let's stop right here and I'll see you in the next video.